Welcome to Exam 1 review, or not Exam 1, well, it kind of is. This is your final exam review, and that is August the 4th, 2016, so that's Thursday. Now, this exam will be a 2-hour exam. There are 60 questions. You will have 15 questions from Exam 1, 15 questions from Exam 2, 15 questions from Exam 3, and then new material, 15 questions. Now remember, if you do well on a certain section, like your lowest grade may be Exam 2, and you do well on the section 2, the 15 questions from the final exam, then that grade for that section can be replace your exam 2 grade. Okay, that's all in the syllabus. So it's very important that you do well on this exam, because not only do you get a final exam grade, but you also get to replace your lowest exam grade. So if you can get all 15 questions, a certain section correct, that would be 100%. Now, what I'm going to do is I've wrote an outline for the 60 questions that you're going to be asked. And I'm going to go through the book intro, and I'm going to tell you page numbers, topics, and maybe even some examples to work. And so if you take notes from this review, you make sure you get those page numbers, those topics and examples, and you focus on those, you should be able to do well on the exam. And you can study those particular topics. Now, I also would print out my old exams, because basically the old exams, Exam 1, 2, 3, we took those questions and those topics and we asked questions regarding those. So that would be a good outline for you to study. Okay, so let's get going. So for Exam 1, you need to understand the states of matter. So section 1.3 and page 5 of the Tro book, the states of matter. You have solid, liquid, and gases, and you need to know their properties. Okay, I'm just going through here. The other question that you need to understand are units of measure, 1.6, page 13. And you get several questions regarding how to do the conversion. So I'm looking at table 1.2, the SI prefixes. It's on page 17. You need how to convert from one unit to the next. You also need to understand volume and density. And that's on page 17 as well. You have to memorize some conversions on table 1.3. I think you need to know 1 inch equals 2.54 centimeters. 1 atmosphere equals 760 millimeters of mercury, which also equals 760 torr. You need to know 1 mile. This was given to you at the beginning. 1.609 kilometer, and then 1 gallon equals 3.8 liters. Let's see what else. So yeah, understand your density formula. So density equals mass over volume. And be able to work example 1.3, calculating density. You need to be able to do section 1.7. Excuse me, sorry about that. Okay, it talks about significant figures. So be able to work example 1.4 on page 21. And you know the rules for counting significant figures on page 22. And be able to work example 1.5 on page 23. You know how to round numbers. So look at the number before. And if it's a 5, you round the previous number up. If it's less than a 5, then you just leave it. The section 1.8 talks about how to do dimensional analysis, converting from one unit to the another. Hopefully you know how to do that by now. But maybe refresh and make sure you understand how to do example 1.7 and 1.8 on page 29, because you will have a few questions that ask you those in particular. Okay, that's chapter 1. Going on to chapter 2. We're still in exam 1. Okay, chapter 2. You need to see the first thing, discovery of the electron. So you need to understand that. So read section 2.4 on page 51. Talks about the electron, the cathode ray. Remember, we're required to give you theoretical questions, not just problem-solving questions. So this is a section 2.4. I would read that section and take notes. It talks about cathode ray, the electrical charge, J.J. Thomson, discovering the electron. Talks about the Millikan oil drop experiment and how that helped with the charge of the electron. And then with this number and knowing Thomson's mass to charge ratio for the electrons, we could figure out the mass in an electron. And then section 2.5 was the Rutherford. What did Rutherford discover? His is really about the nucleus and understand the nucleus has positive charges. And so understand for a theoretical and reading those sections. I would read those, yes. Now, section 2.6 is important because it talks about the subatomic particles, protons, neutrons, and electrons. You're going to need to be able to be given an element off the periodic table and know how many protons, neutrons, and electrons it has, or an ion. So like if you have like sodium plus, how many protons? Well, sodium has 11 protons because it's the 11th element on the periodic table. If its mass is 23, then how many neutrons does it have? Well, what's 23 minus 11? Because it's the protons. So what does the mass equal? Neutrons plus protons. Go back and listen to the recitation videos. So that would be 23 equals neutrons plus 11. And that would be what, 12? N equals 12 neutrons. And the electrons is based on the charge here. And so you have one more proton than electron because protons are positive. So the number of electrons for this would be 10. And so you have to be able to work a problem like that. Also understand isotopes. What are isotopes? There's a picture of Marie Curie on page 58. Talks about isotopes. Isotopes, it's like, so you have like carbon 12, carbon 13, and carbon 14. Well, what all do they have the same? Well, carbon is on the periodic table and it's element number 6. So that means it has 6 protons. The charge, all of these are neutral charges, so they're all going to have 6 electrons. But the number of neutrons for each one of these are going to be different. So the first one's going to have 6, the next one's going to have 7, the next one's going to have 8 neutrons, so the mass is different. So understand what an isotopes are. Okay, on page 59 it talks about ions gaining and losing electrons. That's important. Okay, so you'll get questions like that. Understand page 2.7, understand how to read. You need to know that the first elements are in the group are alkali metals, alkaline earth metals. You need to know which ones are halogens, noble gases, because you need to know these in order to answer questions. You're going to be given questions, and you need to be able to answer that. So read that section. Okay. Section 2.8, you need to be able to calculate, and you had to do this for the first exam, calculate the average atomic mass. And there's an example on page 66. It talks about the atomic mass formula, and then there's actually an example on page 67. It's example 2.5. So be able to calculate the average atomic mass. And then section 2.9 is important. It talks about going for molar mass. Molar mass. Remember, this is a conversion factor. I call it CF. So for 1 mole of something, 1 mole of an element, you have grams of that element. So for 1 mole of oxygen, if you look at the periodic table, you have 16.00 grams of oxygen. And that also talks about Avogadro's number. So 1 mole of oxygen would equal 6.022 times 10 to the 23rd atoms of oxygen. Be able to use those in conversions. Rework those examples. They're associated with this. Example 2.8, 2.7, and 2.8. On page 72 and 73, you will be given questions. The mole concept, example 2.9, I would work all the problems in this section because you will get specific questions. Okay, so that gets us through average atomic mass and going from atoms to number of grams to atoms. Now we're on chapter 3. In chapter 3, we have to understand what an ionic bond is, a covalent bond. It talks about how to write these with lines, what a double bond is and a single bond. Let's see. You have to understand your polyatomic ions. I would be able to work example 3.2 on page 95. How do you know, like xenon is an element, bromine's an element, NO2. How would you name that? You need to know how to name that. That's nitrogen dioxide. How did you know that you needed to name NO2 nitrogen dioxide with the prefix? That's because you have a nonmetal with a nonmetal. They make molecules. Molecules are covalent bonding. If you have a compound like this you have to think about charges. Nickel is a +1, chloride is a 1-, and there's 2 of them. I'm sorry, it's a +2. Nickel is, if you look at the periodic table, you find it, you see that it's a transition metal. I call that a TM. So its charge is going to be based on your anion. There's two of them. So you have a -2, so that, and you only have one nickel, so it's going to be a +2. And this is called nickel. The first element has its name off the periodic table, and then it's chloride. Remember, you drop the INE and add the IDE. You don't put any prefixes like di, because it's charges, and these are ionic bonds. So that's it's important. 3.5, you need to work those examples on writing formulas for ionic compounds and naming ionic compounds. You'll get questions on those. And what about when they have transition metals? You need to memorize your polyatomic ions. Hopefully you already have those memorized. But your polyatomic ions are table 3.5, page 99. Look at those. Memorize the charges and the names and their chemical formulas. You do not need to know hydrated formulas. Molecular compounds. These are a nonmetal with a nonmetal. You have to know your prefixes. You see them right there on page 101. You have the di, the tri, the tetra, the penta. Okay, there's an example there. Example 3.8. How to name these. You do not have to know, you name your oxo acids, so you just need to know binary acids, example 3.9. And then there's a summary, 3.7, on naming these compounds. The last section is 3.8. And we're dealing with formula mass and mole concept. Calculating formula mass, you need to be able to do that. That's example 3.12 on page 107. You need to do the mole concept, converting between mass and number of molecules. You'll get a question like that. That's example 3.13 on page 108. And section 3.9, composition of compounds, mass percent. Yes, you'll have to be able to do that. There's a question on that. So that's on page 109. And you can work your example on page 314, page 110. Be able to work that example. And then it shows you that you could actually use your mass percent as a conversion factor. It's important too on page 112. Okay, so where we are, let me look. We've got, we talked about the electrons and isotopes, proton numbers, neutron numbers, electrons. We've talked about average atomic mass. Talked about molecular formula and empirical formula. Okay, so that is an example. That's where we are. You have to be able to know the difference between a molecular formula and empirical formula. Once again, these questions were on exam 2. So be able to work examples 3.2 and 3.21 on page 118. It talks about your empirical formulas. Understand what empirical formula is. And molecular formula, always pick an example when I memorize something. Water versus hydrogen peroxide. Okay. Water would actually be an empirical formula and a molecular formula. Hydrogen peroxide would be a molecular formula. The empirical formula would be in its lowest terms. And so that would be, you can divide 2 by 2, it would be HO. Okay, so sometimes having an example will help you. Now, writing and balancing chemical equations, you will have to balance in chemical equations. So that might be good for you to read on page 119. And it talks about how to balance equations. So that example 3.22 and 3.23 starts on page 120 on balancing chemical equations. Actually, this is still exam 1. Okay, then we are in chapter 4. Chapter 4 is the beginning of exam 2. And so we start with chapter 4. And in chapter 4, you need section 4.2, stoichiometry. So basically you're going to be given equations and then you have to make conversion factors. And you use the coefficients. So look at example 4.1. 4.1 on page 143. And it talks about photosynthesis and how you can have grams of one element and you can convert it to grams of product. So be able to work those examples. Example 4.2. The more examples on the stoichiometry, the better. Section 4.3, you need to recognize a limiting reagent problem and solve for how much product you would get. Theoretical yield and percent yield. That's on page 145. Work all those examples. You will get particular questions on limiting reagents. How do you recognize them? Well, if you look at example 4.3, and that's on page 149, you see that you're given grams of NO and grams of hydrogen. So you're given grams of both amounts of reactants, and then you have to calculate how much of the product that would be made. So remember, you have to convert each one to moles of the product, and the one with the least number of moles would actually be your limiting reagent. Go back to the recitation problems on chapter 4 and make sure you understand how to solve for limiting reagents. Theoretical yield would be the theoretical yield you get from your the amount of moles or grams you would get from your limiting reagent, and actual yield would have to be given to you. Okay, section 4.4. This is on page 152. This introduces molarity. Remember, molarity is moles of a solute over 1 liter of solution. So be able to calculate the molarity of a solution. Be able to work example 4.5 on page 153. You will get a problem like that on the final. And then example 4.6, you actually use molarity in a calculation. That's on page 154. The next big type, section 4.5. Types of aqueous solutions. You need to know what an electrolyte is versus a non-electrolyte. Remember, we give you theory questions. This is a great theory place where you can look at different compounds like sodium chloride, because it breaks up into its aqueous ions. It's a strong electrolyte and will conduct electricity. You see a sugar molecule there. A lot of times when you have a lot of carbon and hydrogens and oxygens, they form covalent bonds. Okay, they're form molecules. They don't break up into their charges, so they would be a non-electrolyte. Your strong acids break up. So what are your strong acids? That's on page 160. It's very important that you understand table 4.1 on page 161. I do know you'll get several questions where you have to understand your solubility rules. Okay, you'll have to predict you'll have to write a net ionic equation, and you'll have to predict if compounds are soluble. So be able to work example 4.9 on page 162. Be able to write precipitation reactions. Your precipitation reaction, section 4.6 on page 162. And so basically be able to do examples 4.10 and 4.11 on page 165. You'll have to do that for the exam. Writing net ionic equations is on section 4.7, page 167. Be able to do that, and you have an example that I would know how to do, example 4.12 on page 168. The next one. See, so we've done limiting reagents, we've done molarity, precipitation reactions, electrolytes versus non-electrolytes, net ionic equations. You need to be able to do oxidation reduction. So oxidation reduction. Look at section 4.9. Oxidation reduction reactions. Be able to, you're going to have to know oxidation states. Okay, so that's a couple questions right there for exam 2. Rules for assigning. So definitely read this section, page 176 and 177. Be able to work example 4.16 on page 178. Be able to work example 4.17 on page 179. If you do that, you should be fine. Work example 4.18 on page 181. And that gets you through chapter 4 for exam 2. And now we're going into chapter 5. Chapter 5 is the gas law. Okay, so what do you need to know for the gas law? Okay. Well, you need to know the formula. BV equals nRT. You need to know that R is your constant and the gas law constant is, hold on just one second, let's see, 0.08206 liters atmosphere mole Kelvin. And when you know that your N needs to be in moles, your temperature needs to be in Kelvin. So if you get degrees Celsius, you add 273 Kelvin. Your volume needs to be in liters, and your pressure needs to be in atmospheres. So use section 5.1 to understand how to convert pressure to atmospheres. You go to 5.3, that's important. You don't need to know whose law is what, but you better know, look at the graphs. This is a great chapter to learn how to read graphs and put graphics. One of the things we're required to do is put images and graphs and see if you can read graphs and data. So Boyle's law is volume is equal, or let's just say proportional to 1 over pressure. So if you have constant temperature and constant N, then, and you see the graph there, and shows that it's inversely related. That's on page 200. Then you come over to Charles' law, and Charles' law is volume is proportional to temperature, and you see a graph there on page 202 showing as your volume increases, your temperature increases. Be able to read those graphs. Be able to solve for these. So V1 over T1 equals V2 over T2. And you can work the PV equals nRT, so you don't really have to memorize that. P1 equals V1 equals P2 over V2. And so obviously in Boyle's law, N and T are constant here, and in Charles's law, what's constant? P, the other variables, right? P and N. So you can just look at that and figure that out. Okay, and then you have Avogadro's. And Avogadro has volume is proportional to the number of moles. So, and you get a graph there on page 205. So you can see as the volume increases, the number of moles increase, and then V1 over N1 equals V2 over N2. So what's held constant? Well, pressure and temperature, because those are the other two variables that are not present. This all gets you to the ideal gas law on page 5.4. PV equals nRT. Make sure you use the correct units to solve for any of those variables that might be asked. I would be able to work all the examples in section 5.4, so I'd work examples 5.5, 5.6, and then section 5.5, this is STP. Do you remember standard temperature is 0 degrees Celsius or 273 Kelvin, and pressure is 1.00 atmosphere. So at that point, your volume is 22.4 liters per 1 mole of gas at STP. Be able to work those examples in this section. Okay. You'll get a question on partial pressures. So 5.6, page 213, Dalton's law of partial pressures, and the example here is 5.9 on page 514. So I would know how to work those problems. Okay, so let me look. So you need PV equals nRT. You need to be able to solve for the variables. You need to be able to read the graphs and know the relationships for the gas laws. Can you solve for mass? If it asks for mass and you're given PV equals nRT, well, if you need mass, you go and you solve for moles. Okay, and then you can use the periodic table if you're given a gas like xenon. Okay, so that might be helpful. Partial pressures, Dalton partial pressures, and then the last thing you need to know is the kinetic theory. So definitely read section 5.8, kinetic molecular theory. I'd read this like I would study for a history exam because these are good theoretical questions, okay? Kinetic molecular theory. Read the ones in bold on page 223. The size of a particle is negligibly small. These are the assumptions to say that this is an ideal gas, and we can use PV equals nRT. The average kinetic energy of a particle is proportional to the temperature in Kelvin. The collisions of one molecule with another is completely elastic. Okay, elastic means kind of like what you see when you play pool. You hit the pool ball with a certain force, it's going to go equal in magnitude, opposite in direction in the other area. Read on page 224 how Boyle's law, Charles' law, Avogadro's law, and Dalton's law all fall into the kinetic molecular theory, a model for gases. Now, what causes deviation? Deviation is a real gas. real gas, actually has intermolecular forces. And so that's on page 5.10. For a theoretical, that's the opposite of an ideal gas. That might help you answer questions on the kinetic molecular theory. Okay, that wraps up chapter 5. And now we are going to chapter 6, thermochemistry. And we are still, okay, so this is exam 3. Yeah, so this is exam 3, chapter 6. First thing, know your definitions. That's always good. 6.3, internal energy. Which ones are state functions? Table 6.3, be able to apply that on page 254. And there's an example of how you apply that on example 6.1 on page 256. I'd be able to work that equation and calculate internal energy if you're given work and heat. Know which ones are positive and which ones are negative. You also need to know how to calculate pressure. So you have work, pressure, volume work. This is on page 261. I'd be able to work example 6.4 on page 261, where you're calculating work from pressure and changes of temperatures. I would know how to calculate the enthalpy of a reaction on page 267 with the stoichiometry. I definitely read that. When you're dealing with delta H and thermochemical reactions, I would be able to work example 6.7 on page 268. And I would understand Hess's law, which is section 6.8. And Hess's law, a good example of Hess's law is example 6.9 on page 272. I know how to work that problem. Okay, and then if you're given a table of standard enthalpies, could you calculate the delta H? That's 6.9. And you see there's a table 6.5. Of course, you don't have to memorize that. But can you work example 6.10 on page 275? If you could do that, you should be all right. And if you don't see a compound on there like hydrogen gas, H2, that's because it's in standard state, and that would be a 0, right? So read those, and then your formula is on page 276. And so also be able to work example 611 on page 277. And that should get you through chapter 6 for the exam. And now we're on chapter 7. And in chapter 7, you need to be able to calculate the energy associated with wavelengths. So I would be able to do example 7.1 on page 299. I would know my formulas. Energy equals Planck's constant times frequency, and frequency equals lambda, speed of light divided by lambda, which is your wavelength, so then energy equals C over lambda. I'd be able to apply those. Remember, what is Planck's constant? What are the units? That's given to you on your periodic table. Planck's constant is introduced on page 303, and it's 6.626 times 10 to the negative 34 joules times second. So that tells you, and then you also have another constant, which is the speed of light, and the speed of light is in 3.00 times 10 to the 8th meters per second. So it's important that you use seconds for your time, joules for your energy, and make sure your wavelength is in meters. So if you are in nanometers, often you have to convert to nanometers. Now remember, this is the energy for one photon of light. So when you're given one photon of light and you calculate that energy you can go ahead and convert it to, that's the energy for one photon of light. So I know a lot of times the questions will ask for mole of energy. Okay? So then you have to do Avogadro's number. Okay, so don't be fooled. Make sure that you do 6.022 times 10 to the 23rd photons of light for 1 mole of light. I think you have some examples, so work examples 7.2 and 7.3 on page 304 and 305. The next questions that you'll have to do with Bohr. Now, this is also another good area where we don't have to ask you to calculate things for the most part. So definitely read 7.3, page 306 and 307. Be able to understand about atomic spectra and emission spectra. Also page 7.4, page 309. The uncertainty principle through page 313. That's important. Read those for questions. Okay. And you could get some theory questions there. Now, talking about quantum numbers. Be able to know what the names of the quantum numbers are. So you have them defined here on page, they're basically, read about 315. Talks about the quantum number n and l and m sum l and m sum s. You're going to get lots of questions on these. These are important numbers, okay? So know that the n is your principal quantum number. L is called your angular momentum. M sum L is your magnetic, and this is your spin. So when the questions are asking you those, you need to understand what they relate to. N is your energy level. This also coincides with the rho of the periodic table. Be able to relate these to the periodic table. L, always think of your shape. So if L equals 0, then your shape is an S sphere. If L equals 1, then you have the dumbbell shape, and it's on the different axes, like the P of Y, P of X, and P of Z. And why are there 3? Because your M sub L gives you 3, and then just like this goes, L equals 1 is also a letter named P. That's your P shape for the probability of finding the electron in this electron density. But M sub L has 3 numbers, but then they are -1, 0, and +1. Okay, so M sub L here depends on your L of 0, and it would just be 1, and it would be a 0. And that's important when you're given the quantum numbers that things are allowed to be. You can also see on page 316. So definitely work all these examples. Example 7.6 on page 318. The shapes of the atomic orbitals, that's important. That's kind of what I'm talking about here. 7.6, page 321. Read that. 322, 323, 324, 325. And that finishes you up with chapter 7. And now we are going on to chapter 8. Chapter 8, you need to be able to write electron configurations. So chapter 8, you need to be able to write electron configurations. We're looking at section 8.3 on page 337 now. So it talks about electron spin, Pauli exclusion. Read those sections. I kind of visually have page 341 memorized, figure 8.5. It's important because you have to know how to fill your orbitals. Work example 8.1 on page 344. Be able to do that. Be able to work example 8.2 and 8.3 on these pages. You're going to have to be able to look at the orbital blocks of the periodic table. That's worth a good question there. So be able to look at figure 8.7 and be able to work example 8.4 on page 348. That's worth a question. Also, I don't know where it talks about isoelectronic. We talk about isoelectronic elements in your recitation. I'm looking for the word isoelectronic in your book. You need to be able to write electron configurations for different ions. Ions include cations and anions, and then find what their isoelectric. That would mean they would have the same exact electron configurations. So be able to do that. The other thing you want to be able to do is the periodic table. So I would understand my trends on section 8.6. Trends in atomic radius. That's important. Ions. This is important too. 8.7 section 8.7 355. Paramagnetic. Understand what paramagnetic is. That means that the electrons are unpaired, or at least one electron is unpaired, and that would make it magnetic. If it's diamagnetic on page 356, that means all the electrons are paired. Zinc atom is diamagnetic and therefore does not have magnetic properties. Work example 8.6 on page 356. Understand ionization energy. You do get some questions about your first ionization energy. Basically, you want to write the electron configuration and understand those trends of why an atom would want to hold on to its electrons more so than the others. And it's all about trying to get that complete octet, right? Being isoelectronic with your noble gases. So a lot of your trends are visually shown to you for ionization energy on page 360. Electron affinities. I would read section 8.9 and try to understand how group 1 and group 2 and group 7 behave with regards to wanting to hold on to their electrons. Okay, now we're into the last 15 questions of exam 4 that you're going to see. So exam 4, there's 15 questions. Exam 4, your final exam, those 15 questions. Okay, they're going to come from chapters 9 and 10. So, hold on just a second. And I will try to help you the best I can with what to pay attention to. All right. First thing, you need to be able to write Lewis dot structures. Okay, so 9.4. And be able to work example 9.1 on page 385. Be able to write the Lewis symbols for your different, they're showing you calcium and chlorine. Be able to answer questions about lattice energy. Remember, we have to ask questions about such things. So I would read lattice energy, and I would know my trends on page 388. So read about your trends on page 388 and be able to do example 9.2 on page 389. Okay. Because you will get some questions on lattice energy and Lewis dot structures. Now, they're talking about 9.5 single covalent bonds, double and triple bonds. You will need to recognize that something like this is a single bond, this is a double bond, and this is a triple bond. And the trends, remember, short and strong. So we'll also talk about this in chapter 10, but this would be, so if you have it, let's say you have a hydrogen there. You have hydrogen here. And this, you have hydrogen. I'm going to tell you something here. So this is, there's 4 groups on this carbon. So that's going to be hybridization sp3. Because remember, these got to add up to 3. 3 plus 1 is 4. So this is an sp3 plus an sp3. This is an sp2 with an sp2. And this is an sp with an sp. You see how there's the superscripts add up to 2? Look at that carbon. There's one thing there and one thing there. So that's just 2 things. Now, the S has a spherical, and the P has like a dumbbell shape. Now, when you merge these 2 together and you hybridize them, an sp3 would have more like a shape like that. You see how you got maybe 3 times as much P as you do the S? It's kind of like a wiffle ball bat, right? And you get 3 of those. Well, 4 of those. Here, this would have 2 times as much P character. So maybe it gets bigger with the S. And then here, SP, you would have 50% S and P. So the point is, when you have 50% S character, it's going to be shorter. It's going to be a shorter bond. Short and strong. Short and strong. So these triple bonds are short and strong bonds. They're short. Or if you get a question about length, a triple bond is going to be shorter, and it's going to be stronger. Short and strong. And I'm just showing you the hybridizations because they got 50% S character. This guy only has 33.3% S character, and this one with the single bonds only has 25% S character. S character, S. S character, S. Short, strong. Okay. Anyway, I brought that up because I'm just looking at your single and double and triple bonds on page 391 and 392. It's important that you understand that. Okay, electronegativity. We're looking at section 9.6, electronegativity and bond polarity. You will get several questions on this. Louis Pauling, this contributed to his Nobel Prize on page 395. He came up with electronegativity, and you need to know this trend. Increasing electronegativity goes up a group and over. So fluorine has a 4.0 electronegativity. Francium down here in the corner has a 0.9. Electronegativity is kind of like, I think of, what do you call that, when you're tug of war. So it's within a bond polarity. So if you have hydrogen bonded to fluorine, well, fluorine has a 4.0, hydrogen's over here with a 2.1, I believe, yes. So you're going to have, in this bond here, you're going to have more pull towards fluorine. Fluorine is more electronegative. So it's going to be pulling the electrons. So you know that hydrogen and fluorine, to make up this bond, has 2 electrons, right? Well, they're not just equally between the two. It's going to be more like this. Within this bond, it's going to be closer to fluorine. And that's one way to make things an acid, because an acid is an H+, right? And it leaves without its electrons. So within a bond, you have electronegativity. So bond polarity, dipole moment, those are important on page 396 and 397. To be able to do example 9.3, 9.4, 9.5. These are on page 398, 399. You will have to write Lewis structures, okay? So know those examples. I worked through those. I told you write the skeletal structure number 1 where you put your most electropositive element in the center. So if it asks you for the correct Lewis structure, just take those molecules and go through your procedures. 1, you write down the structure. You put the most electropositive element in the center. Then the second thing you do is you calculate the total valence electrons. If the total valence electron's wrong, then the Lewis structure is wrong. Okay? Remember, neutral has just the total. If it has an ion, then you've got to account for those electrons. And then you make sure that every element has a complete octet, right? Now there are exceptions, and you're going to run into them. So your exceptions are, let's go ahead and find what your exceptions are. Just go ahead and memorize them. They're on page 9.9. Exceptions, you got odd. So if you have an odd number when you calculate your total valence electrons, that's going to be an exception to the octet rule. An incomplete octet, okay? By the way, nitrogen, because it's 5, valence number 5, you typically get the odd with nitrogen. Incomplete, boron and aluminum. These typically are incomplete. Hydrogen makes a duet, right? So you got to recognize that. And then expanded octet. So you see here on page 408 you have an expanded octet like sulfur, and these are N equals 3 or greater. Okay. Be able to calculate formal charge. So not only do you write the Lewis structures, be able to do that, you need to be able to calculate formal charge. And the example formal charge is on page 403. And it gives you the formula for formal charge, and be able to work example 9.8 on page 404. And be able to practice that. Practice those. Practice example 9.1 on 409. Read those. And then your next one, you'll get some questions about bond energies and bond lengths. This is page 409. You're looking at 9.10. And there's some trends there. So look at your bond length here on page 413. And look at recitation. Notice that the double and triple bonds are shorter bond lengths than a single bond. And I was trying to tell you that about the S character on page 413. So your double bonds and triple bonds are going to be shorter. If they're shorter, they're stronger. Look at your more electronegative bonds. That's what you're looking on the next table. You got nitrogen bonded to fluorine, chlorine, bromine, or iodine. So fluorine is more electronegative, and therefore it's going to be a shorter bond length. Shorter bond length is a stronger bond. Okay? And you don't have to worry about that last section. That gets you through chapter 9. And then chapter 10 is really about the molecular and electron geometries. So you need to be able to do valence shell electron pair repulsion theory. So the first thing you do always is you write a correct Lewis structure for the molecule. Okay? So that's the first thing you do. And we've told you how to do that. Look at the recitation videos where you put the most electropositive as your central atom. You add up all your total valence electrons, and then you make sure every atom has a complete octet. Okay? Now there are the exceptions. There's just a few of them, right? So, and those exceptions can apply, and that would be a correct Lewis structure. Now, once you do that, then you assign the geometry, because, and this is about assigning the geometry, the shape of the molecule. And you have to basically memorize the table on page 434. 434, table 10.1. And so you're going to have questions that say predict the electron geometry, predict the molecular geometry. Okay, electron geometry, if you notice that there's two bonding groups, it doesn't matter how many, it's just how many things there are. So you either have two groups, so here, even if you have something like this molecule here. And remember, you only really care about the central atom, okay? So here you have two groups. Oh, okay, so let's look at sulfur here. Actually, sulfur has three groups here. You have this lone pair here. You have a single bond to oxygen, and you have a double bond to oxygen, but you treat double bonds and single bonds as a group, okay? So there's three groups. So in this case, three groups will tell you it's electron geometry. And so three groups you need to memorize are trigonal, planar, and that's basically 120 degrees. So there's three groups, it's trigonal, planar. Now, when you're looking at molecular geometry, you got to consider the lone pairs. Now, if there's no lone pairs, your electron geometry is going to equal your molecular geometry. In this case, then it will be bent. So you're going to have to make sure you know how to work those problems. We work those problems in our recitation. I would work examples. Example 10.2. Example 10.3 on page 436. Predicting molecular geometries. Shape and polarity. Okay, so now we're looking at section 10.5. You need to be able to figure out the polarity. So you look at your central molecule. I would be able to work example 10.5 on page 441. And you want to be able to predict if something's polar. If it has lone pairs on the central atom, it's going to be polar. I think Pauline gave you 3 Pauline rules for polarity. If you're like BClF2, if you work out if you work this out, the Lewis structure, you will see that this is its Lewis structure. And when you do that, you'll see that this is a polar molecule because fluorine and chlorine are different. So actually it would end up being like this, and there would be the polarity within that molecule. If you have lone pairs on your central atom, you're going to have a polar molecule. That's important to be able to determine whether you have polar molecules or nonpolar molecules. Okay, so now I'm going to look through what I wrote down for Chapter 9 and Chapter 10. Lewis dot structures of the elements and ions, lattice energy, polar bonds, electronegativity differences, know your trends, know the short bonds or strong bonds, Lewis structures, be able to choose correct Lewis structures. If there's a charge on your molecule, then you need to accommodate that for your valence electrons. Be able to calculate formal charge. Be able to apply which elements have higher electronegativities. Be able to apply ionization energies for the first one. Is your molecule polar? That's what we're talking about now. You have to be able to draw the Lewis structures and then look at your central atom. Be able to predict electron geometry of molecules and molecular geometries. Another thing, be able to count how many pi bonds there are in sigma bonds. So let's look at benzene. Benzene is C6H5. So what does benzene look like? I'll draw the Lewis structure for benzene. There's 6 carbons, and every other carbon has a hydrogen and a double bond. Okay, so what's the number of pi bonds? And what's the number of sigma bonds? So pi bonds and sigma bonds in this molecule in benzene. Well, the sigma bonds connect they're single bonds. Okay, sigma bonds are single bonds, and they connect every element together. So what do you have? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That would be 12. And then how many pi bonds would be the double bond? So you'd have 1, 2, 3. In that case, you'd have 3 pi bonds. Be able to work a problem such as that. Hybridization is important. You have to be able to predict the hybridization of each element. That's on page 445, valence electrons and hybridization. It talks about how to get sp3 hybridization, sp2, sp. It talks about the bond shapes. Excuse me. And the requirements for hybridization, like triple bonds. Excuse me. Triple bonds need 2 unhybridized p orbitals. So be able to apply table 10.3 on page 456. Be able to work examples 10.6 and 10.7 on page 457. And example 10.8 on page 458. And then the last thing you need to be able to do is section 10.8, and this is molecular orbital theory. And in you got to be able to fill in your electrons for an anti-bonding orbital and bonding orbitals and calculate bond order. The good news is you will be given the energy diagram such that you would see on example 10.9, but be able to work example 10.9 on page 462. You'll also be given an energy diagram such as on page 465, so you don't have to memorize that. Sometimes you have to memorize them for these. So the good news is you don't have to for your exam. it's provided for you. Be able to work example 10.10 on page 468. Example 1011 on page 470. And the other thing I want you to be able to do, so be able, when you work these, be able to do bond orders. And also, I'm going to stress for you to read page 467 and be able to predict the paramagnetic and diamagnetic from these molecular orbital theories. And you also have a couple of questions on your recitation, chapter 10, that dealt with that. And if you do all those examples, you should get them all correct. So good luck to you, and I hope everybody does well.